So now we're going to look at some examples on how to apply the conservation of mechanical energy. The first example is something very familiar. We've already done it multiple times, and I promise this will be the last method we'll be using to solve this simple problem. The reason why, again, I do this is because I want you to compare different methods on how to solve the same problem and see the pros and cons, and of course, to make sure that our new method gives you the same result as it should. So it's a free fall problem, assuming that we have something of mass m. It's going along a straight line, vertical straight line in a free fall, either up or down. In this case, I chose the initial direction of motion to be downwards with a speed of v initial. And the question is, after it descends by distance h, what is its final speed? Now, you'll recall that we did this first in chapter 2, because it's a uniformly accelerated motion, so we have method A is v final squared minus v initial squared equal to 2a delta x. A is g, delta x is just h, so you get v final equals the square root of v initial squared plus 2gh, a very familiar result, right? Very familiar result. And in chapter 7, we revisit this problem as the first example of chapter 7, and we said, we're going to apply the work energy theorem, okay? The work energy theorem, and that for that you identify initial and final state, and you go v initial, you go wi to final equals delta k, the change in kinetic energy. So in this case, so I'm going to write down equals delta k, and the work done is only by gravity, and it's mgh, of course. And that equals the change in kinetic energy from final to initial to final. So that's 1/2 mv final squared minus 1/2 mv initial squared. And you come up with the same answer. V final equals to the square root of v initial squared plus 2gh. Okay, the masses cancel out. So the third and final method is the conservation of mechanical energy. Now, first of all, mechanical energy is conserved. You have to make sure that's the case before you can apply it, of course. And that is because the only force in this question is the gravitational force, which is a conservative force. So we know we have the conservation of mechanical energy. Now, even though the answer is the same and it's quite simple to obtain, the idea is different, because now we start with E initial equals E final. Okay, so I'm going to use a different color for this new method. E initial equals E final. And E is the total energy, it's the sum of kinetic and potential energy. The kinetic, so I'm going to write K initial plus U initial equals K final plus U final. Okay, K initial equals 0 because it's not moved. I'm sorry, it's not 0. It is 1/2 m v initial squared. Okay, now U initial, the gravitational potential energy, initial value, what is that equal to? Well, it depends on where you set the 0 of the potential energy to be. Okay, and let's say, you know, we're going to set the 0 of the potential energy right at the bottom. Okay, at this level, we can call it, let's say this is where UG is set to be 0. Okay, we'll put the 0 level at the bottom of the drop, and then since the initial position is distance h above it, then the gravitational potential energy initial value would be equal to mgh. Now that equals to the final k plus final f, and you notice here we did not have to worry about any work done. Just E initial equals E final. So for K final, that is 1/2 mv final squared. And for U final, what is that equal to? Well, didn't we set it to be equal to 0, right? We set U final equal to 0. And that's why U initial equals mgh. So that's just a 0, okay? And with that, we can easily solve for V final, and you can clearly see it's the same result as before. So you can solve for V final by crossing out 1/2 m, and then you can take the square root, you get V final. So it's very simple to do. V initial squared plus 2gh. So the same result. But the thinking, again, the thinking is a little different. We don't worry about things like work. We just equate enough initial energy with final energy. And in this case, notice that for the gravitational potential energy, I can set a 0 wherever I want. And I chose to set 0 at the final position. And you got to be consistent, because if you did that, you have to, then the initial potential energy has to be mgh, because again, it is a distance h, vertical distance h above the 0 point of the potential energy. Okay, so that's our first method. And it doesn't really give you a much faster answer than the other two methods, but at least it establishes this way of doing things, a new way of doing things, and it does give you the same result. All right. Now, let's look at our second example. So the second example is a little bit more interesting. I have two masses, two blocks, M1 and M2, and they're linked by a massless string over a frictionless pulley. Okay, and mass 1 initially rests on an incline, which makes an angle theta with the horizontal, and mass M2 is being supported by a spring at the bottom, and also it's being pulled by the string which connects to M1. Now, initially, nothing is moving. And we also assume that initially the spring K, the spring of spring constant K, is at its natural length, meaning that it is neither stretched nor compressed initially. Okay. Question is, if I let go of it, then M1 and M2 both will start to move, right? Assuming that M1 is heavy enough so that M1 is going to go down the slope while M2 is going to go up. Okay, once you let go from rest. Question is, after they both go by a distance x, okay, so M1 goes down the slope by distance x, and M2 goes up by distance x. At that point, I want to know how fast both blocks are moving. I want to know the speed v. Okay, I also want to know the value of x such that the speed will reach a maximum value in a subsequent motion. So I'm looking for the moment where they both reach the same maximum speed. Okay, because look, initially the speed is going to be 0, right? You just let go because that's where we started from rest. And then they're going to start to move, so obviously the speed will pick up. But eventually, when M1 goes down far enough and M2 goes up far enough, at some point it's going to stop, right? So the speed starts from 0 and goes up, and then it goes back down to 0. So clearly it has to reach a maximum value at some point. So I want to know what that point is. I also want to know what that maximum speed is equal to. Okay, so this is what I want to do for this problem. Now, assuming that there's no friction anywhere, of course, that's given in a problem statement. Okay, there's no friction on the slope and on the pulley anywhere. And there are two forces doing work. Okay, one is gravity, and the other is the force of the spring. Okay, now don't worry about the tension. The tension does work for M1. It also does work for M2, and these two works cancel out. Can you see that? All right, because M1 and M2 move together with the same speed. All right, so there's no net movement along the direction of the tension. So don't worry about the tension here. It doesn't do any net work. So as a result, the only two forces doing work, gravity and elastic force, since they're both conservative forces, I can safely apply the conservation of mechanical energy. So let's do that. Okay. So first question. Okay. The first question, they want to know a v at x, and that is, what is the speed v of both blocks when they have moved by a distance x? What is that equal to? Okay, again, apply conservation of energy. This is particularly useful here for this problem because we're dealing with a variable force in a case of a spring. You don't want to deal with a variable force with Newton's second law because that complicates the matter. So we can bypass that. We don't have to use Newton's second law. We just relate initial with final energy. and then we don't have to get into the force directly. Okay, so E initial equals E final. E initial is when initial state is when everything gets started, and final state is when both blocks have moved by a distance x. Okay, so what is E initial equal to? Well, there are in general 3 terms in energy. There is kinetic energy, K initial. There is gravitational potential energy initial, UG initial. And there is elastic potential energy initial. Okay, what is that equal to? That's going to be equal to the sum of these 3 terms in the final state. So K final plus UG final plus UE final, right? Okay, so what is K initial equal to? That's obviously 0, because we said it starts from rest. What is UG initial equal to? What is the initial value of the gravitational potential energy? Well, again, that depends on where you set the 0 to be, okay? So here's the deal. Why don't I just set the initial gravitational potential energy to be 0? I can set a 0 anywhere I want. I set the initial state to have 0 gravitational potential energy. And then with that in mind, if in a final case, in a final state, an object moved up by a distance h, then it gains potential energy of mgh. If it goes down by a distance h, then it loses potential energy of mgh. Okay, so that is what I decided to do. I'm going to call this 0. And what about UE initial? Well, initially, the spring is neither stretched nor compressed, so we typically choose this as the origin of the potential energy curve for elastic energy. So this is usually set as the 0 of the potential energy, the elastic potential energy. So you know what? All 3 terms are 0 initially. So the total energy is 0. Okay, so might as well just write a separate line, E initial equal to 0. E initial equal to 0. And okay, so what's E final now? So E final, again, the sum of these 3 terms, 1/2 mass times speed squared, that's kinetic energy. Remember, these 2 pieces are connected by the same string, so therefore they have the same speed, m1 plus m2. E final squared, that's the kinetic energy term, okay? That's the kinetic energy term. And then the potential energy term, the gravitational potential energy term. Now be careful here. We started out with the 0 point of gravitational potential energy. Look at what happens to M1. M1 went down, right? How much did it go down? Well, I can draw a little diagram here. You can see how much it went down. This is M1 initial to final. This distance, the hypotenuse is x, and the distance that it went down vertically, if this angle is theta, h equals x times sine theta, and that's going downwards. So therefore, it lost potential energy by how much? By m1gh, where h equals x times sine theta. Okay, so it's minus m1gh. Again, h is x sine theta. This is the amount of energy change, the gravitational potential energy change for m1. In the meantime, m2 went up by distance x. That's a vertical ascent. Therefore, its potential energy goes up by m2gx. Okay, there's no sine theta here. That's it. That is the gravitational potential energy, the final state. Plus, don't forget, the elastic potential energy final state. Now, in a final state, when m2 goes up by distance x, the spring has been stretched by the same amount. So the final potential energy for the spring is 1/2 kx squared, right? And since E initial is equal to E final, I'm going to equate them, okay? I'm going to equate these 2 terms. All right, so therefore, I end up with the following. I end up with, this whole thing, E final equals E initial, and that's a 0. Okay, so I'm going to isolate that out. Okay, I'm going to isolate that out now. So that is the equation from which I can find the final speed. Okay, that V final is the speed of the system, both for M1 and M2, as they have moved by distance x. Okay, you can easily solve for that, right? That's not a problem. Just isolate for V final and just solve it. I trust you can easily do that. Now, question is, you know clearly as x changes, v final is also going to change, right? V final is also going to change. And we know that V final went up to, start from 0, went up to a certain value, maximum value, and went down back to 0 when both blocks reach a temporary stop. Again, I'm looking for the maximum value of V final, or V in general. And I also want to know what happens, what is the X value when that happens? Okay, so part B, that's a little bit more interesting. V maximum equals what? And at what value of X does this happen? Is V equal to V maximum? Okay, so that's what I want to know. That's the second problem. Now, there's a purely mathematical way of doing that. I'm going to start with this first, and also we'll look at, from a physics point of view, how does that make sense? Well, why do I say that? It's because, look, we already found this expression V final, right, as a function of X. I mean, we didn't isolate V final, but we can easily do that. So as X changes, so does V final, and V final is a function of X, which satisfies this equation right here, this equation right here, okay, this equation. And if you have a given function, how do you find the maximum value of this function? Well, all you have to do is set a derivative equal to 0. Here, V final, or let me just call it V from now. It's a function of X, right? It's a function of X. And if you want to find the maximum value of V final, all you have to do really is set dV over dx equal to 0, okay? So mathematically, here's how we can come up with our answer now that we already know V as a function of X, okay? So set, oops, you're going to just set V final equal to 0, dV final over dx equal to 0. That's what you want to do. Or dV dx equal to 0. Let's see how we can do that, okay? Go back to the equation, the boxed equation. I'm just going to take a derivative with respect to X for every term. I mean, you can solve for V final first, but that's not necessary, okay? So the first term, what you're going to get is 1/2 m1 plus m2, 1/2 m1 plus m2, and then times the derivative of dv squared over dx, and that is 2v dv dx, right? That's the first term. The next term is negative m1g sine theta, these are all constants, dx dt. I'm sorry, dx over dx, just dx over dx, okay, which is just 1, so might as well just erase that. That's not necessary, okay? And then plus the next term, which is just m2g, and then you have another term left, and that is 1/2 kx squared. You take a derivative, you're going to get 1/2 k times 2x, okay? And that equals 0, because the other side equals 0. And remember, we're going to set dv dx equal to 0, okay? That's what we set out to do. I'm going to set this equal to 0. So this tells me that whenever you see this term, you're going to set it to 0. Okay, so the first term disappears, right? The first term, because the first term is 0, this is 0. Okay, and so what do you have left? What you have left is the sum of the next 3 terms. So therefore, you get negative m1g sine theta plus m2g plus kx equal to 0. So this is the equation for x. What is the special value of x? This is the x that will give you the maximum speed for both blocks. So after they move by this distance x, we call it, why do we call it x1, okay? At x equal to x1, v becomes v maximum. So what is x1 equal to? Well, we just solve for x1 from this equation. And what is v maximum equal to? Well, solve for x1 and plug x1 into this equation in the box. Because at this value of x1, v is v maximum. Okay, I trust you can do the algebra, but that's not very important at this point. Okay, so And then, so V max equals to the value of V at x1. Okay, just plug in V x equals x1 into the equation in the red box. And you're going to find the maximum value of V in a subsequent motion. Right? So that is how we do the second part of the problem mathematically. But I'm not happy with that just yet, because after all, this is a physics problem. I want to make sure that we can all understand what's going on, and better yet, we can come up with a simpler, cleaner way of solving the same problem, along with a better understanding of what's going on. Okay, so from a force point of view, because we analyzed this situation with the conservation of energy alone. Okay, but from a force point of view, initially, you look at M1 and M2 as one system. Now you can do that because they have the same acceleration, they're linked by the same string, and therefore I can think of M1 plus M2 as a system. Okay, so think of, I'm gonna use a different color to indicate this is a different method utilizing our physics. So think of M1 plus M2 as a system. Okay, what is the net force driving the acceleration for this system? Well, we know it's going to move along, the direction of M1 going down hills. So I'm going to call that direction positive. So therefore, there's a component of mg which provides a positive acceleration, but it's going to be resisted by the weight of m2 and also the force of the spring. Both of these forces will retard the motion. Okay, so the net force along the direction of motion would be a component of mg. And what's that component, by the way? That is m1g sine theta. We all know that, right? We all know that. Starting from chapter 5, we're in how to find this component, m1g sine theta. That's the component of the gravitational force along the slope. And that is, again, that is the force that drives the system, that accelerates the system. But m2g is the weight of the second block. It resists the motion, it resists the acceleration, and also the force of the spring also resists the acceleration. They're both negative, so minus m2g. Then minus kx. Okay, that is the net force. Now, what is that equal to? That equals mass times acceleration, m1 plus m2 times acceleration. Okay, the acceleration both m1 and m2. Now, we're looking for the maximum speed. The maximum speed happens when the acceleration equals what? Equals 0, because acceleration is how fast the velocity changes. And if that rate is 0, that means the velocity is either maximum or a minimum. Okay, the derivative dv dt equals 0, which means the velocity is either maximum or minimal. So when you set acceleration equal to 0, this is where you're going to get a maximum velocity. Okay, as a matter of fact, if you take a closer look at this expression for f net, all these are constants on the left-hand side except for x. Everything else is a constant. So, but x is not. X is not a constant. Okay, so as time goes by, x increases, everything else is the same on the left-hand side, and therefore, initially when x is pretty small, f net is going to be positive, and that's the reason why. That is the reason why the system starts with m1 going down slope. Okay, with m1 going down slope because m1 is pretty heavy, and gradually as they go further and further down, x becomes greater and greater and greater. Remember, there's a negative sign in front of it, okay? So at some point, the negative kx term becomes large enough so that the entire expression on the left-hand side, which is f net, start to turn its sign. It went from positive to 0 and eventually to negative. When f becomes negative, that means the thing is going to slow down, okay? Because you have a negative acceleration. So you start with a positive acceleration, which becomes smaller and smaller and smaller, and it temporarily becomes 0 and then become negative. Okay, so before the acceleration turns negative, it's always positive, which means the thing keeps on going faster and faster. So clearly, the maximum speed is reached when the acceleration is 0, and that is to say that f net equals 0. Okay, so you can set f net equal to 0. to obtain x1 at which v equals v maximum, okay? Because before that point is reached, it keeps on accelerating with a positive acceleration. After that point is reached, the acceleration becomes negative and the thing slows down. Okay, so all you have to do really is set this equal to 0. So therefore, the condition for maximum speed is m1g sine theta minus m2g minus kx1 equals 0. That's how you find x1. But you see, that's the same exact expression that we got before, right here. The same exact expression. See, these two are the same exact expression. Okay, the first expression we'll obtain right here comes from what? Come from setting the derivative of the energy, derivative of every term of the energy expression with respect to x as 0. So it's a pure mathematical way of finding the maximum value of x, maximum value of v. But the second method carries distinct physical meaning because all we have to do really is to set the total force equal to 0. And that is the reason why you have a maximum speed, because that's where the force turns from acceleration to a deceleration as it turns signs. Okay, so either method gives the same answer, but the second method certainly is preferable as a solution to this physics problem. All right, so that's the part B of the problem. Now you can also look at part C, which is relatively simple as well. So for part C, you want to go a little further. You want to ask, at what value of x are these two blocks going to reach a temporary stop? Because as you know, you cannot keep on going down forever, right? At some point, they're going to stop. What is the value of x such that they will stop for the time temporarily? Okay, that in fact is quite straightforward. All we need to do really is just to set the final speed to 0. Okay, that's all we have to do. But I'm going to do this anyways, just to complete this problem. So see, at what x, or at what value of x do they stop? So all you have to do is set v equal to 0 in the equation in the red box, okay? Equation in this red box right here. So then I have, there's no first term anymore, okay? There's no first term anymore. Then I have negative m1 g x sine theta. And that's the first term. And then the next term is plus m2 gx. And then plus 1/2 k x squared. That equals 0. Okay. All I did was to set v equal to 0. Now, you notice that this is not the same equation as the one that gave you maximum speed. No. This is the one that gave you maximum speed. This one. It's not the same as the very last equation, which gives you the value of x when the whole thing stops. So one is maximum speed, one is the stop. So it's a totally different story. Okay, you can see they're different. I can cross out a power of x in the last equation. There is an x in every term, but still the answer is different because there is a 1/2 factor of 1/2 in the last expression for x expression. There's a 1/2 here. Okay, you know what that means? If I call this distance x2, okay, x2. x2 and x1 are different. In fact, x2 is 2x1. Interestingly enough, right? Because there's a extra 1/2 here. Okay, so you know what that means? It means that if I let go of the system, m1 is going to go down, m2 is going to go up. And as they travel distance x1, they reach the maximum speed. And after that, they're going to slow down. And when the distance traveled becomes x2, they stop. And x2 is twice as long as x1. Okay, so let's say you found that after traveling 3 centimeters each, the speed peaks out. And after traveling another 3 centimeters, guess what? They stop. Okay, why is x2 equal to twice as x1. This is a mathematical observation in our case, right? But it has interesting physical meanings. To see the clear meaning of that, you have to wait a little bit longer. When we study the oscillation in the next course, you can analyze the situation more carefully, and you will find why is it that in extreme position, the displacement is twice as much as the displacement to the point of maximum speed. It actually carries a physical meaning as well. Okay, so this is how we find the solution to this problem using the conservation of energy. And this method really is the best to solve this problem, because otherwise, if you use Newton's second law directly, you're going to have to deal with this variable force, k times x. As x changes, the force also changes. That's not something you want to deal with unless you don't have another choice. Okay, so that's the second problem, second sample problem. Now, let's look at the final sample problem, this one. So what we have here is a block which is compressed against a spring, okay? So you compress the block against the spring. Actually, you compress the spring against the block. You compress spring with this block. You start from here and move. You push the block towards the wall, so the spring is compressed by an amount x. Okay, by an amount x this way. And then you let go of the block. Of course, it's going to then accelerate forward, right? And it will reach the bottom of this circular loop at point A. So it enters this circular loop at point A with a speed VA. Okay, you can find what VA is, and then it proceeds to climb this circular track frictionlessly. Okay, there's no friction anywhere. Then when it reaches the top of the circle at point B, it's upside down. The speed reduces to VB. You can also find VB. Okay, now the first question is, what is VA equal to? And the second question is, in order to be able to complete circular motion around this circular track, what is the minimum value of x? How much should I compress the spring to the smallest possible amount so that this block can barely complete the circular motion? Okay, now the thing about this problem, which makes it valuable, which makes it distinct from the problems before, is that there is a special moment, special position or state, which is at the top of the track. In order to complete the circular motion, you know it has to be able to make it to point B, right? Once it can clear point B, the rest of the job is simple. So there's a special moment, point B, that you have to analyze. And if you only analyze one moment or one state, which is a point B in this case, you cannot use a conservation law, because conservation laws relate to states. This point B is only one state. If you only want to know what happens with one state, conservation law itself doesn't give you the answer. But it doesn't mean conservation law is useless for this problem, because in order to start from the initial position where the spring is compressed to the final position where the block is the point B, you have to relate them by conservation of energy. Okay, so that's a problem which combines Newton's second law and the conservation of energy. That's why it's a valuable problem. So let's look at how we do this problem. Okay, part A of this problem. What is VA equal to? Now that's a piece of cake, assuming, of course, there's no friction anywhere. Okay, otherwise you cannot even use conservation of energy. And it just set initial energy to be equal to final energy. In this case, the initial energy is when the spring is fully compressed, and it has only elastic potential energy, is 1/2 k x squared. Okay, it doesn't move yet. There's no kinetic energy, and as far as gravitational potential energy, the initial position here and the final position there, they're at the same level, so they have the same amount of gravitational potential energy. We might as well call both of them equal to 0. It doesn't really matter. Okay, so which is we're just going to ignore that, because remember, what's important is the change in potential energy. And as far as the gravitational potential energy is concerned, it doesn't change going to point A. Therefore, I'm going to ignore that. Okay, so this is the initial energy that that's all there is to it. The final energy is when it reaches point A, there is only what? Kinetic energy, 1/2 m VA squared. So you can easily find VA now, okay? Piece of cake, this is VA equals to the square root of, okay, equals the square root of K over M then times X. Okay, again, we bypassed the complexity of this variable force of the spring, and we got the answer directly. So this is the cleanest way to find VA. This is just conservation of energy. Now, the second part of the problem, what is the minimum amount of compression X so that the thing can complete a circular motion about this vertical track? Okay, so clearly you have to analyze what happens at point B. Okay, so at B, we can analyze the motion of this block at point B using Newton's second law. So what's going on at point B? Well, it's moving at the speed VB, so it's doing circular motion with a speed VB. Therefore, there has to be centripetal acceleration, which is VB squared over R, right? The centripetal acceleration requires a centripetal force. So who is providing this block with a centripetal force? Well, the centripetal force is the net force pointing from the block to the center of the circle. At this moment, look at the forces acting on this block at this moment. You have mg going downwards. You can also have a normal force from the track pushing you down. And guess what? Both of these forces, mg and n, at this moment, they happen to point from point B to the center of the circle, point O. And therefore, it's the sum of mg and n that equals the centripetal force. Okay, so you can write down mg plus n. The sum equals what? M times centripetal acceleration, which is m VB squared over R. Okay, now clearly, the greater the speed VB, the greater the value of n, the normal force, okay, to balance this equation. But I'm looking for the minimum amount of compression X here, minimum amount of compression that I can get away with to complete the circular motion. Therefore, I'm looking for the minimum possible value of VB, okay? And that happens, you look at this equation here, that happens when the left-hand side of this equation is minimized. Here's the left-hand side of the equation, right here. Left-hand side of the equation. mg cannot change, it's always mg, but n is adjustable, okay? To find minimum value. So for minimum X, you want minimum VB, which means you want to set n equal to what? 0. So because it's just about to lose contact with the track, okay? It's going so slowly that just about to, to lose track. Literally, to lose contact with the track. So set n equal to 0. This tells me that mVB squared over R equals to mg. This, in fact, is the minimum value of VB you can get away with, okay? So minimum. And this minimum VB corresponds to minimum amount of X, because the less amount of compression, the slower it's going to go at point B. So now what we need to do is to relate the initial position, which is the fully compressed position of the spring, with the final position, which is at point B. Okay, so how do we do that? Well, you can relate these 2 points with the conservation of energy. Initially, the energy is, so E initial equals E final. The initial energy is, there is no kinetic energy for the block yet, and there is no gravitational potential energy. We can set the gravitational potential energy to be 0 at that level, so you're going to have only 1/2 kx squared. This is the amount of initial energy. This is X minimum, because I'm looking, this X minimum corresponds to VB minimum. Okay, so that's it. That's E initial. What's E final? E final is when you're at moving at point B. Okay, there is 1/2 VB squared. Okay, VB squared, and it's not just any VB, it's VB minimum. Okay, plus there is no elastic potential energy because the spring has been completely decompressed. But then there is also a gravitational potential energy. Remember, initially, when you're at this level, you call the potential energy 0. Gravitational potential energy, that's why we didn't even write down the gravitational potential energy initially. But the final position is a distance 2r above it, right? This distance is not 2r above it. Okay? So therefore, the final potential energy, the gravitational potential energy, is mg times 2r. Right? That's conservation of energy. So you see, we've got two equations. One is Newton's second law applied to point B. Okay, so that is that equation. Secondly is the conservation of energy, relating the initial state to the final state at point B. You need to combine both of these in order to find x minimum. And the math, whatever is left, is quite simple. I have 1/2 k x minimum squared equal to 1/2 mvb minimum squared, but mvb minimum squared equals mgr. So this is just mgr. mgr plus another 2 mgr. Okay, then I can find x minimum. So x minimum. What is that equal to? It is equal to the square root of 3 mgr over k divided by 2. So it's actually there's a k here and there's a 6. Okay, so this is 6 right here. That is the minimum amount of compression the spring must have in order to push the block so that it can barely make its way around this vertical circle. Again, this problem is different from the previous ones in the sense that you need to analyze a special point B at the top of the track using Newton's second law, and then you combine that with the conservation of energy, which takes the block from initial state to the final state at point B. That belongs to a class of problem in which both Newton's second law and the conservation of energy must be utilized. Okay, and in the next lecture, which is also the last lecture, we're going to look at a case where there is a non-conservative force at play, more than one non-conservative force at play, so that energy, the mechanical energy system, is not quite conserved. It does change. So how do we deal with situations like that? We'll see that in the next lecture.